2.5 million light-years away, something is watching us back. The Andromeda Galaxy holds 1 trillion stars within its spiral arms. At its core sits a black hole 140 million times more massive than our Sun. The James Webb Space Telescope just peered into its heart with infrared eyes, and what scientists discovered has rewritten everything we thought we knew about our galactic neighbor. A sleeping monster is showing signs of waking, ancient scars from galaxies it devoured. Evidence that our collision with this cosmic titan has already begun. If you enjoy what comes next, hit that like button and subscribe. We begin now. On clear autumn nights, you can see it with your naked eye, a faint smudge of light in the constellation Cassiopeia. Most people walk right past it, unaware they're looking at a galaxy containing 1 trillion stars, all packed into a spinning disk 220,000 light-years across. The Andromeda Galaxy, our nearest major galactic neighbor, and it's coming straight toward us. For over a century, astronomers have studied this cosmic island. They've mapped its spiral arms, counted its star clusters, and measured its distance at roughly 2.5 million light-years from Earth. That sounds impossibly far, yet in cosmic terms, Andromeda is practically in our backyard. The Milky Way and Andromeda are the 2 largest galaxies in what scientists call the local group, a collection of more than 50 galaxies bound together by gravity. But here's what makes your spine tingle. Andromeda isn't standing still. Every second, it races toward us at roughly 70 miles per second. That's over 250,000 miles per hour. At that speed, you could circle Earth 10 times in 60 minutes. The galaxy has been on this collision course for billions of years, and nothing in the universe can stop what comes next. The James Webb Space Telescope changed everything when it turned its golden mirrors toward Andromeda. Unlike Hubble, which sees visible light the way human eyes do, Webb sees in infrared heat signatures, hidden structures, things that have been invisible to every telescope that came before. When Webb focused on Andromeda's core, scientists expected to see a sleeping giant, a quiet galactic center minding its own business across the void. They were wrong. What Webb revealed sent shockwaves through the astronomical community. The images showed something stirring at the heart of Andromeda: unusual bursts of radiation, distorted clouds of gas, structures that shouldn't exist according to standard models. One researcher described the data as deeply unsettling. Another called it the most significant discovery about Andromeda in decades. The telescope captured details no human instrument had ever seen before. Filaments of superheated material spiraling inward, dust rings glowing with infrared light, star clusters behaving in ways that defied explanation. And at the very center, wrapped in layers of gas and ancient stars, sat the monster itself, a supermassive black hole that might be waking up. The implications are staggering. If this black hole is increasing its activity, it could reshape the entire galaxy before our 2 cosmic islands ever collide. But the truly terrifying part? What Webb discovered suggests the collision between Andromeda and the Milky Way might be more violent, more chaotic, and closer than anyone predicted. Your eyes are liars. They show you less than 1% of what actually exists. The visible spectrum, the rainbow of colors you see every day, represents just a thin slice of electromagnetic radiation. Beyond violet lies ultraviolet, X-rays, and gamma rays. Beyond red lies infrared, microwaves, and radio waves. Most of the universe operates in frequencies you'll never see. That's where the James Webb Space Telescope enters the story. Launched in December 2021, Webb doesn't see the universe the way you do. Its instruments are tuned to infrared wavelengths, the heat signature of the cosmos. This gives Webb a superpower that Hubble never possessed. It can peer through cosmic dust that blocks visible light completely. Think of it like this. Imagine trying to see through thick fog with your eyes. Impossible. Now, imagine having thermal vision that detects heat instead. Suddenly, the fog becomes transparent. That's exactly what Webb does when it looks at galaxies like Andromeda. When Webb pointed its 6.5-meter mirror at Andromeda, it saw structures that had been hidden for billions of years. Dust lanes that appeared dark and empty in visible light suddenly blazed with infrared energy. These lanes aren't empty at all. They're packed with cool stars, molecular clouds, and organic compounds, the kind of material that builds new solar systems. The telescope uses two main instruments to dissect galaxies. The near-infrared camera, called NIRCA, captures sharp images of stellar populations. The mid-infrared instrument, known as MIRI, detects cooler objects like dust, grains, and aging stars. Together, these tools create a complete portrait of a galaxy's hidden anatomy. But here's where it gets strange. When scientists examined Webb's infrared data from Andromeda's core, they noticed something peculiar: temperature variations that made no sense. Regions that should be cooling down were instead heating up. Gas clouds showed unusual motion patterns, spiraling inward faster than gravitational models predicted. Confirmed observations revealed dust rings surrounding the galactic center, glowing brightly in mid-infrared wavelengths. These rings aren't uniform. They have gaps, distortions, and clumps that suggest recent disturbances. Something has been stirring up material in Andromeda's core within the last few million years. In cosmic time, that's yesterday. Webb also detected specific chemical signatures that previous telescopes missed: entirely complex carbon molecules, organic compounds, elements forged in the hearts of dying stars and scattered across the galaxy. The infrared spectrum acts like a barcode, telling scientists exactly what elements exist and in what quantities. The detail is breathtaking. Webb can resolve individual star clusters in Andromeda that Hubble could barely distinguish as blurry dots. It can measure the temperature of gas clouds down to fractions of a degree. It can trace the spiral arms deeper into the galaxy than ever before. Yet, with each new layer of detail comes new questions. The more clearly we see Andromeda, the less we seem to understand about what's happening at its core. And that invisible monster lurking in the center? Webb just gave us our first real look at what it's doing. What scientists found there defies everything they thought they knew about dormant black holes. Numbers lose meaning at galactic scales. Your brain cannot truly comprehend what 1 trillion means. If you counted one star per second without sleeping or stopping, it would take you 31,700 years to count them all. That's how many stars burn inside Andromeda right now. Each one is a nuclear furnace. Most are smaller and cooler than our sun. Some are massive blue giants that will explode within a few million years. Others are ancient red dwarfs that will burn for trillions of years into the future. All of them orbiting a common center of gravity, held together by the invisible hand of dark matter that outweighs the stars themselves by 6 to 1. The James Webb Telescope can resolve individual stars in Andromeda's outer regions. Not all of them, of course, that would be impossible. But Webb can pick out the brightest giants, the massive stars that shine with the power of 10,000 or even 100,000 times the luminosity of our Sun. These stellar beacons serve as markers, allowing scientists to map the galaxy's structure in unprecedented detail. Hubble photographed over 200 million stars in Andromeda during a survey that took over a decade. Those images created the most detailed mosaic of another galaxy ever assembled. But Hubble operates primarily in visible light. It saw the bright young stars and missed countless others hidden by dust. Webb is now filling in the gaps, revealing the cool red giants and the dusty stellar nurseries where new stars are forming. Star formation in Andromeda happens differently than in the Milky Way. Our galaxy produces roughly 7 new stars per year. Andromeda creates fewer, perhaps 2 or 3. Scientists theorize this difference comes from Andromeda's violent history. The galaxy appears to have undergone a major collision several billion years ago, an event that used up much of its available gas. With less raw material, fewer stars can form. But Webb discovered something unexpected. Certain regions of Andromeda are creating stars at surprisingly high rates, far exceeding what models predicted. These stellar nurseries hide in the spiral arms, wrapped in thick cocoons of dust that visible light telescopes cannot penetrate. Webb sees right through them. The temperature readings are particularly revealing. Newborn stars are hot, blasting their surroundings with ultraviolet radiation. This heats up nearby dust, causing it to glow in infrared wavelengths. Webb can measure this glow and calculate how many young stars must be present. The numbers are higher than expected in several key regions. Why would certain parts of Andromeda suddenly become more active? One theory points to gravitational interactions with satellite galaxies. When a small galaxy passes close to Andromeda, its gravity compresses gas clouds, triggering bursts of star formation. Another theory suggests that Andromeda's own spiral arms create compression waves that periodically squeeze gas into dense clumps. The sheer mass of all these stars is staggering. Andromeda contains roughly 1.5 trillion times the mass of our Sun, counting both the stars themselves and the dark matter halo surrounding them. The Milky Way, by comparison, holds only about 800 billion stellar masses. Andromeda is nearly twice as massive as our home galaxy. This size difference matters greatly. When two galaxies collide, the larger one usually dominates. And in 4 billion years, when these two cosmic titans finally meet, Andromeda will be the bigger predator. But there's something else lurking at the center of all those stars. Something that makes the trillion burning spheres look tiny by comparison. At the exact center of Andromeda, in a region smaller than our solar system, sits an object that weighs more than 100 million suns combined. It's invisible. It emits no light. It's a supermassive black hole. And for most of human history, it has been asleep. Black holes don't actually sleep, of course, but they can be quiet or loud depending on how much material they're consuming. When a black hole actively feeds on gas and stars, it becomes one of the brightest objects in the universe. The infalling matter heats to millions of degrees, creating a blazing accretion disk that screams across every wavelength from radio waves to gamma rays. Astronomers call these active galactic nuclei, and they can outshine their entire host galaxy. Andromeda's black hole is not like that. For millions of years, it has been classified as dormant. It sits there, warping space-time into an inescapable pit, occasionally snacking on a stray gas cloud or unlucky star. The radiation it produces is faint, barely detectable even with powerful X-ray telescopes. Scientists compare it to Sagittarius A*, the supermassive black hole at the center of the Milky Way, which is also remarkably quiet. Then came the X-ray observations that changed everything. The Chandra X-ray Observatory has been watching Andromeda's core since the year 2000. For over 15 years, it recorded a steady but dim X-ray signal from the central black hole. Occasionally, the signal would spike a brief flare, lasting hours or days, then back to baseline. These flares happened every few years and seemed random. In 2006, Chandra detected an unusually strong flare. The X-ray brightness jumped by a factor of 100, flooding the central region with high-energy radiation. Then it faded again. Scientists filed it away as interesting, but not alarming. Black holes burp sometimes. Maybe a small gas cloud fell in. Maybe a star wandered too close. But in 2013, it happened again. Another powerful flare. And this time, something strange accompanied it. The Ice Cube Neutrino Observatory in Antarctica detected a burst of neutrinos coming from the direction of Andromeda. Neutrinos are ghost particles that barely interact with matter. They're produced in extreme environments, places where matter is being torn apart under unimaginable forces. The correlation was unsettling. 2 X-ray flares, 2 neutrino bursts, both coming from the same source, both suggesting that something violent was happening at Andromeda's core. Recent analysis published in 2025 confirmed that the black hole has remained in an elevated state of activity since 2006. The baseline X-ray emission is higher than it was before. The flares are more frequent. This is confirmed data. The black hole is behaving differently than it did 20 years ago. The question is why? One theory suggests that Andromeda recently captured a dense gas cloud or possibly a small galaxy remnant. As this material spirals toward the black hole, it would produce exactly the kind of elevated activity scientists are seeing. Another theory is more disturbing. Perhaps the black hole is naturally cycling into an active phase. Perhaps what we consider dormant is just the calm before the storm. If the black hole is truly waking up, the consequences would ripple across the entire galaxy. Jets of radiation could blast through Andromeda's core. Star formation could be suppressed or triggered depending on the intensity. And when the Milky Way finally collides with Andromeda billions of years from now, we might be facing not one, but 2 active supermassive black holes. The James Webb Telescope added another piece to this puzzle. Its infrared observations revealed something Chandra couldn't see. Gas clouds near the black hole are moving faster than they should. Something is accelerating them. And the most terrifying question of all remains unanswered. If this black hole is waking up now, what will it look like when it reaches full activity? When you pack enough matter into a small enough space, you rip a hole in the fabric of space-time itself. That's what sits at the center of Andromeda, a supermassive black hole with a mass estimated at 140 million times than our Sun. To understand how monstrous this is, consider the black hole at the center of our own galaxy. Sagittarius A times weighs roughly 4 million solar masses. Already an incomprehensible object, already powerful enough to fling stars around at thousands of miles per second. Andromeda's black hole is 35 times more massive. The event horizon, the point of no return around a black hole, expands with mass. For Sagittarius A*, the event horizon has a radius of about 12 million miles. You could fit 17 suns side by side across that distance. Andromeda's black hole has an event horizon roughly 35 times larger. The sphere of doom surrounding it stretches over 400 million miles across. That's wider than the orbit of Mars. Anything crossing that boundary is gone forever. Not destroyed instantly as science fiction sometimes suggests, but stretched and shredded by tidal forces as it spirals inward. Physicists call this spaghettification. A human falling toward the black hole would be pulled apart, their feet experiencing far stronger gravity than their head, until they were torn into a stream of atoms. But nothing is falling in right now. The space around Andromeda's black hole is remarkably empty. This is why it stays so quiet. A black hole without fuel is just a gravitational well sitting in the dark. Scientists measured the mass of this monster by watching how stars near the galactic center move. These stars orbit at incredible speeds, thousands of miles per second, whipping around the central point in elliptical paths. By tracking their motion over years, astronomers can calculate exactly how much mass must exist at the center to produce those orbits. Scientists using combined data from Hubble and the Spitzer Space Telescope had previously glimpsed hints of these structures. But Webb's images are the clearest view yet. The filaments look like cosmic waterfalls, streams of matter pouring toward the center from multiple directions. Some originate from dense molecular clouds in the galactic disk. Others come from disrupted star clusters that wandered too close. The feeding process isn't continuous. It happens in bursts. A large clump of gas falls in over the course of weeks or months, causing a spike in radiation. Then the black hole goes quiet again as it waits for the next meal. This is confirmed by the X-ray observations, showing sporadic flares every few years. What makes the current situation unusual is the increased frequency of these feeding events. Over the past 2 decades, the black hole seems to be snacking more often. This suggests something has changed in the central region. Perhaps gravitational interactions from Andromeda's satellite galaxies are funneling more gas toward the core. Perhaps the galaxy's spiral arms are compressing material and sending it inward. Webb's infrared data showed another disturbing detail. Some of the filaments are moving faster than expected. The gas is accelerating as it approaches the black hole, which is normal, but the speeds measured are higher than gravity alone should produce. This hints at additional forces at play, magnetic fields perhaps, channeling the gas along specific paths, or jets of material being blown out from the black hole's poles, creating pressure that pushes nearby gas around. Near the very center, within a few light years of the black hole, the filaments become chaotic. The orderly spiral breaks down into turbulent eddies and swirls. This is the accretion zone, where material is moving at significant fractions of light speed, heated to extreme temperatures and torn apart by tidal forces. Even Webb cannot resolve details this close to the event horizon. The region is too small and too bright. But the outer filaments tell the story clearly. The black hole is being fed slowly for now, a trickle rather than a flood, yet the feeding rate is increasing. More gas is finding its way to the center than was arriving 100 years ago. If this trend continues, Andromeda's black hole could transition from dormant to moderately active within the next few million years. In cosmic time, that's imminent. For humanity, it's so far in the future that our species may not exist to witness it. Unless, of course, the feeding accelerates faster than predicted. Unless something catastrophic happens to dump a massive amount of material into the core all at once. And when the Milky Way collides with Andromeda in a few billion years, that's exactly what will happen. When Hubble first photographed the center of Andromeda in 1991, astronomers couldn't believe what they saw. Instead of one bright nucleus, there were two distinct concentrations of light separated by roughly 5 light-years. The brighter one, labeled P1, sits slightly off-center. The dimmer one, called P2, occupies the true center of the galaxy. For years, this double nucleus sparked heated debate. The most popular theory suggested Andromeda had recently cannibalized a smaller galaxy, and P1 was the remnant core of that victim, a captured nucleus orbiting the true center before eventually being torn apart and absorbed. It was a dramatic explanation that fit with the evidence that large galaxies grow by eating smaller ones. But this theory had problems. If P1 was a captured galaxy core, it shouldn't be stable. The tidal forces from Andromeda's main black hole would rip it apart in just a few million years. Yet P1 appeared intact and organized. The timescale didn't work. Further observations with improved instruments revealed the truth. P2, the dimmer concentration, is where the supermassive black hole actually resides. It's surrounded by a compact disk of hot blue stars. These stars are spectral class, A young and massive, and they emit strongly in ultraviolet light. In blue and ultraviolet images, P2 appears brighter than P1. In red and infrared images, P1 dominates. So what is P1? The answer turned out to be more interesting than a captured galaxy. P1 is part of an eccentric stellar disk that orbits the black hole. The stars in this disk don't travel in neat circles. Their orbits are stretched into long ellipses. As they move around the black hole, they bunch up at the apocenter, the point farthest from the center. This creates a concentration of stars that appears as a separate, bright region. Think of it like cars on a racetrack with a sharp curve. The cars slow down as they enter the curve and bunch together. From above, you'd see a concentration of vehicles at that spot. The same thing happens with stars in eccentric orbits around Andromeda's black hole. But why would stars orbit in such bizarre patterns? The leading explanation is gravitational recoil from a black hole merger. When two supermassive black holes spiral together and collide, they release gravitational waves. These waves carry momentum. And if the two black holes have different spins or masses, the merged black hole can be kicked in one direction. This kick disturbs the orbits of nearby stars, flinging them into eccentric paths. Computer simulations support this idea. When astronomers model a black hole merger at the center of a galaxy, the resulting stellar distribution looks remarkably similar to what we see in Andromeda's core. The merger would have happened several hundred million years ago, long enough for the system to partially settle, but not long enough for the eccentric orbits to decay into circles. This means Andromeda's central black hole is itself a product of collision. It likely formed when two smaller black holes, each weighing tens of millions of solar masses, merged into the current monster. And if Andromeda's black hole has already undergone one merger, it will certainly undergo another in 4 billion years. When the Milky Way and Andromeda collide, their central black holes will eventually spiral together. The 4 million solar mass black hole from our galaxy will meet the 140 million solar mass giant from Andromeda. The collision will release gravitational waves so powerful they'll ripple across the universe. But we're getting ahead of the story. First, you need to understand how Andromeda became the monster it is today. And that means looking at the scars it carries from its violent past. Galaxies are not peaceful places. They're battlefields where gravity reigns supreme. The strong consume the weak, the large devour the small. Andromeda is no exception. It's a cannibal that has been feeding on its neighbors for billions of years. The evidence is written in the stars themselves. Astronomers studying Andromeda's stellar populations discovered something remarkable. The galaxy's outer halo, the diffuse cloud of old stars surrounding the main disk, contains distinct streams of stars moving in organized patterns. These streams are not random. They're the shredded remains of smaller galaxies that Andromeda captured and tore apart. When a dwarf galaxy falls into the gravitational well of a giant like Andromeda, tidal forces stretch it into a long ribbon. The galaxy's stars are stripped away over millions of years, spread out along its orbital path. Eventually, the dwarf galaxy disappears completely, its stars absorbed into the halo of the larger galaxy. But the stream they create can persist for billions of years, a ghostly marker of what once existed. Scientists using the Hubble Space Telescope mapped dozens of these stellar streams in Andromeda's halo. By analyzing the ages and chemical compositions of the stars in each stream, they reconstructed the galaxy's merger history. What they found was shocking. Andromeda has consumed at least 100 to 200 smaller galaxies over the past 12 billion years. Some were tiny dwarf galaxies containing only a few million stars. Others were substantial spiral galaxies with billions of stars. The most significant merger happened relatively recently in cosmic terms, just a few billion years ago. This collision brought a massive influx of stars and gas into Andromeda, triggering bursts of star formation and completely reshaping the galaxy's structure. Evidence for this event shows up in the ages of stars. Many of Andromeda's stars are between 2 and 4 billion years old, suggesting a major episode of star formation during that period. But there was another merger, much older, that happened roughly 10 billion years ago. This ancient collision involved a galaxy, perhaps 1/5 the mass of the Milky Way, a substantial meal. The stars from this merger now form part of Andromeda's inner halo, a spherical cloud of old, metal-poor stars surrounding the galactic center. The chemical signatures tell the story clearly. Stars born in small dwarf galaxies have different element ratios than stars born in large galaxies. Small galaxies form stars slowly, so their stars are enriched primarily by long-lived, low-mass supernovae. Large galaxies form stars rapidly, so their stars contain elements from massive, short-lived supernovae as well. By measuring these ratios in Andromeda's halo stars, astronomers can identify which galaxy each star originally came from. This is confirmed data. The stellar streams exist. The chemical evidence is unambiguous. Andromeda has been violently assembling itself for over 10 billion years, and the process is still ongoing. Right now, several dwarf galaxies orbit Andromeda. They're doomed. Over the next few billion years, they'll spiral inward, stretched and torn apart by tidal forces, until nothing remains except new streams in the halo. Andromeda will continue growing, feeding, preparing for its ultimate collision. The Milky Way isn't innocent either. Our galaxy has its own history of cannibalism. We're currently in the process of consuming the Sagittarius dwarf elliptical galaxy, a small system that has already made multiple passes through the Milky Way's disk. We'll finish eating it within the next few 100 million years. But when Andromeda and the Milky Way finally meet, it won't be a small galaxy being devoured by a large one. It will be two titans locked in mutual destruction. Both galaxies will be forever transformed, and the scars they leave on each other will persist for billions of years. The ghosts of dead galaxies are watching. They know what comes next. Imagine tearing apart a city brick by brick and scattering the debris across 1,000 miles. Years later, a detective could still reconstruct what happened by analyzing the patterns in the rubble. That's what astronomers do when they study galactic halos. The halo of Andromeda extends far beyond the bright spiral disk visible in photographs. It stretches outward for hundreds of thousands of light years, a vast, nearly invisible sphere of old stars and dark matter. This halo contains the memories of every galaxy Andromeda has ever consumed. Using deep imaging from the Hubble Space Telescope, a team of astronomers cataloged the globular clusters in Andromeda's halo. Globular clusters are dense balls of ancient stars, typically containing hundreds of thousands of members packed into a sphere just a few dozen light-years across. They orbit galaxies like satellites, immune to the chaos of the galactic disk below. Andromeda has over 400 of these clusters, far more than the Milky Way's roughly 150. Each cluster tells a story. By measuring how fast it moves and in what direction, astronomers can trace its orbit backward in time. Clusters that orbit in similar planes and at similar speeds likely came from the same original dwarf galaxy. The halos of consumed galaxies don't disappear immediately. When Andromeda tears apart a dwarf galaxy, the victim's dark matter halo, its globular clusters, and its stars all get redistributed. But they maintain some coherence for billions of years. They move as a group, orbiting Andromeda in patterns that betray their origin. In 2019, astronomers published a groundbreaking study revealing that Andromeda's globular clusters separate into two distinct populations. One group orbits in a relatively flat plane, moving in the same direction as the main galaxy's rotation. These are likely native clusters, born when Andromeda itself formed over 12 billion years ago. The other group moves on, wildly inclined orbits, some even going in the opposite direction. These are the invaders, clusters captured from smaller galaxies, but it gets more specific. The captured clusters themselves split into two subgroups based on their orbits and ages. One subgroup appears to be the remnants of a merger that happened roughly 2 billion years ago. The other subgroup is much older, dating back to a merger around 10 billion years ago. Two distinct cannibalistic events, each leaving a unique signature in the halo. This is galactic archaeology. By studying the present-day distribution of stars and clusters, scientists reconstruct the violent history that created the galaxy we see today. It's like excavating ancient ruins to understand a civilization that disappeared millennia ago. The stars in these ghost halos are metal poor, meaning they contain fewer heavy elements than stars born recently. This makes sense. Small dwarf galaxies form stars slowly, so they don't produce as many heavy elements through supernovae. When Andromeda absorbed these galaxies, it inherited their metal-poor stars, which now populate the outer halo. Webb's infrared observations added new details to this story. By measuring the temperatures and compositions of individual red giant stars in the halo, astronomers can determine their ages more precisely. Some stars are over 12 billion years old, nearly as ancient as the universe itself. Others are just a few billion years old, born during relatively recent mergers. The spatial distribution matters too. Stars from the most recent merger are concentrated in specific regions of the halo. Stars from the ancient merger are spread more evenly, having had billions of years to disperse. All of this paints a clear picture. Andromeda is a serial killer of galaxies. It has been hunting and consuming neighbors for its entire existence, and it shows no signs of stopping. Right now, multiple dwarf galaxies orbit within its gravitational reach, spiraling slowly inward to their doom. The Milky Way is heading straight into the jaws of this predator. But unlike the dwarf galaxies Andromeda has consumed before, our galaxy has the mass to fight back. What happens when two equal predators meet? Over 400 globular clusters orbit Andromeda like a swarm of ancient bees. Each cluster is a city of stars, hundreds of thousands of them bound together by gravity in a sphere that could fit inside the distance from our Sun to its nearest neighbor. These clusters are relics from the early universe, formed over 12 billion years ago when the first galaxies were assembling. Globular clusters are among the oldest objects in the cosmos. The stars within them are metal-poor, born before the universe had been enriched with heavy elements from multiple generations of supernovae. They shine with a dim reddish light, the color of aging giants that have burned through most of their hydrogen fuel. Andromeda has far more globular clusters than the Milky Way. Our galaxy hosts roughly 150 confirmed clusters. Andromeda has over 400, possibly closer to 500 when you count the faintest ones. This difference is significant. The number of globular clusters a galaxy possesses correlates with its merger history. More mergers mean more clusters. Each time Andromeda consumed a dwarf galaxy, it inherited that galaxy's globular clusters. Small dwarf galaxies might contribute just a few clusters. Larger galaxies could bring dozens. Over billions of years, Andromeda accumulated a vast population from its cannibalistic conquests. The most massive globular cluster in Andromeda is designated B23 G78. It contains several million stars and likely harbors an intermediate mass black hole at its core, weighing close to 100,000 solar masses. This cluster is so dense and massive that it might actually be the stripped core of a small galaxy that Andromeda devoured long ago. When a dwarf galaxy is torn apart, sometimes its central nucleus survives as a dense stellar remnant. Webb's observations are helping scientists study these clusters in new ways. Infrared imaging can penetrate the dense cores of globular clusters and resolve individual red giant stars. By measuring the brightness and color of these giants, astronomers determine the cluster's age and chemical composition with unprecedented precision. The orbital motions of these clusters reveal Andromeda's dark matter distribution. Dark matter is invisible, but it exerts gravitational pull on everything around it. By tracking how globular clusters move over years and decades, scientists map the invisible dark matter halo that dominates Andromeda's mass. This halo extends far beyond the visible galaxy, stretching perhaps 1 million light-years into space. But here's where things get unsettling. Some of Andromeda's globular clusters are moving faster than they should. Their velocities suggest they're being influenced by gravitational perturbations from something we can't see. The most likely explanation is ongoing interactions with infalling dwarf galaxies. As a dwarf galaxy spirals into Andromeda, its gravity tugs on nearby globular clusters, accelerating them into unusual orbits. This means the merger process is active right now. Andromeda is currently in the act of consuming at least one, possibly several small galaxies. These victims are in various stages of destruction. Some are mostly intact, still recognizable as distinct objects. Others have been stretched into long streams, their stars spread across hundreds of thousands of light-years. Eventually, they'll all disappear into Andromeda's halo. The clusters themselves will survive. Globular clusters are incredibly resilient. Their stars are packed so tightly that the cluster holds together even when subjected to strong tidal forces. They can pass directly through the disk of a galaxy and emerge on the other side intact. When Andromeda and the Milky Way eventually collide, the globular clusters from both galaxies will intermix, creating a new population numbering over 500. For now, these ancient clusters orbit Andromeda in silent testimony to the galaxy's violent history. They're the gravestones of dead civilizations, markers of galaxies that no longer exist, and they're a preview of what awaits the Milky Way. When our galaxy falls into Andromeda's gravity well, our globular clusters will join theirs, swirling together in the merged halo of a new cosmic monster. The collision hasn't started yet. Or has it? Andromeda doesn't travel alone. It moves through space with an entourage of at least 14 satellite galaxies, all trapped in its gravitational grip, slowly spiraling toward their doom. The largest is Messier 32, orbiting just 24,000 light-years from Andromeda's center. Scientists believe it was once a full spiral galaxy, but repeated passes through Andromeda's disk have stripped away its outer regions, leaving only the dense core. Another prominent satellite is Messier 110, orbiting much farther out at 190,000 light-years. Unlike most elliptical galaxies, it still shows signs of recent star formation, likely triggered by gravitational interactions with Andromeda. Then there are the ultra-faint dwarf galaxies. These tiny systems contain only a few thousand stars and are dominated by dark matter at ratios of 100 to 1 or higher. Here's something strange. Several of these satellites orbit in a coherent plane called the Great Plane of Andromeda. Why would they arrange themselves in such an organized pattern? One theory suggests they're remnants of a larger structure that Andromeda disrupted long ago. Regardless of how they got there, their fate is sealed. They're spiraling inward, and tidal forces will eventually tear them apart, spreading their stars across Andromeda's halo. For several satellites, this process has already begun. For decades, astronomers described the Andromeda collision as a distant future event, something 4 billion years away. That description is no longer accurate. In 2020, Project Omega made a startling discovery while mapping Andromeda's halo of hot ionized gas. The halo extends roughly 1 million light-years from the galaxy's center in all directions. The Milky Way has a similar halo, also reaching about 1 million light-years. Here's the problem. Andromeda is only 2 million light-years away. If both galaxies have halos extending 1 million light-years in all directions, then the halos are already touching. This is confirmed observational data. The collision between the Milky Way and Andromeda has already started. We're currently passing through the outer reaches of Andromeda's halo, and Andromeda is passing through ours. The gas is incredibly thin, barely a few atoms per cubic meter, so we don't notice it. But make no mistake, these two cosmic islands are gravitationally bound, locked in an inexorable dance that will end in merger. Computer simulations show what comes next. In roughly 2 billion years, Andromeda will appear much larger in Earth's night sky, stretching across tens of degrees. By that point, tidal forces will be distorting the Milky Way's spiral arms. In roughly 3.7 billion years, the first close approach happens. The two galaxies will swing past each other, their disks beginning to interpenetrate. This will trigger massive bursts of star formation as gas clouds collide and compress. The night sky will blaze with millions of newborn blue stars. After the first pass, the galaxies will swing apart, then collide again more violently. The spiral structures will be completely disrupted. Stars will be flung in all directions. Some solar systems will be ejected into intergalactic space, orphaned from any galaxy. By roughly 7 billion years from now, the merger will be complete. The two galaxies will have combined into a single elliptical galaxy. Astronomers have already given it a name, Milky Way, but recent research has added uncertainty. A 2025 study found that when you account for the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, the probability of a collision drops to roughly 50%. There's a real chance the two galaxies will swing past each other and never fully merge within the next 10 billion years. 4 billion years seems impossibly distant. To put it in perspective, 4 billion years ago, Earth was a barren rock with no life. But Earth won't survive that long anyway. In roughly 1 billion years, our sun will be about 10% brighter, triggering a runaway greenhouse effect. Earth's oceans will evaporate. Within a few 100 million years, Earth will resemble Venus, scorched and lifeless. By the time of the collision, Earth will be long dead. The habitable zone will have moved outward to Mars or Jupiter's moons. Or perhaps life will have migrated to a different star system entirely. If the collision happens, the night sky will be transformed. Andromeda will stretch from horizon to horizon. The two galaxies will interpenetrate like ghosts. Individual stars won't collide, space is too empty. But the gas will collide, triggering millions of new stars. Our sun will likely survive unscathed. However, our orbit will change dramatically. We'll be flung much farther out, perhaps 50,000 light-years from the new galactic center. There's even a 12% chance we'll be ejected entirely, becoming intergalactic wanderers. At the very center of the merged galaxy, the two supermassive black holes will spiral toward each other over millions of years. When they finally collide, they'll release a burst of gravitational waves powerful enough to be detected across the universe. That collision is still billions of years in the future. Or maybe it isn't. Recent data has introduced doubt. What if the galaxies miss each other entirely? The collision is no longer certain. But one thing remains true. Andromeda is heading toward us. We're heading toward it, and we're already passing through each other's cosmic atmospheres. When two supermassive black holes collide, reality itself shivers. The fabric of space-time ripples outward in waves of gravitational energy, traveling at the speed of light across the universe. This isn't science fiction. This is confirmed physics predicted by Einstein over a century ago and directly observed by the LIGO and Virgo detectors in 2015. The Milky Way's central black hole weighs roughly 4 million times the mass of our Sun. Andromeda's weighs 140 million solar masses. When these two monsters finally spiral together, the merger will release more energy than all the stars in the observable universe combined, at least for the brief moment of collision. But getting to that point takes time. Black holes don't simply crash together. They orbit each other, slowly spiraling inward as they radiate gravitational waves. This process can take hundreds of millions of years. When the two galaxies first collide, the black holes will be separated by tens of thousands of light years. They'll begin a long, slow dance toward the center of the merged galaxy, driven by dynamical friction, the gravitational drag caused by passing stars and gas clouds. With each pass, they move closer together. Eventually, when the separation drops to a few light years, gravitational wave emission becomes the dominant force. The black holes spiral faster and faster, whipping around each other at significant fractions of light speed. In the final seconds before merger, the two black holes will be orbiting each other hundreds of times per second. If humanity still exists and still builds telescopes, this will be the astronomical event of the millennium. The collision itself lasts only a fraction of a second. The two event horizons touch and merge, creating a single, larger black hole. But the merger isn't clean. The combined black hole will be violently spinning and highly distorted. It will ring like a bell, oscillating as it settles into a stable configuration. The final mass will be roughly 144 million solar masses. However, a small amount of mass, perhaps 1 to 5%, will be converted directly into gravitational wave energy during the merger. This energy radiates outward at light speed, carrying information about the masses, spins, and orbital parameters of the black holes. If the two black holes have different spins, the merger can produce a recoil kick. The merged black hole can be ejected from the galaxy center at speeds of hundreds or even thousands of miles per second. If this happens, the resulting galaxy would have no central black hole for millions of years until the kicked black hole eventually falls back to the center. The surrounding gas will be disrupted as well. Any gas orbiting one of the original black holes will be stirred up by the merger. This could trigger a burst of accretion onto the newly formed black hole, lighting it up as an active galactic nucleus. For a few million years, the center of Milky might shine as brightly as a quasar, outshining the combined light of all its stars. This is the fate awaiting the cores of the Milky Way and Andromeda. Two black holes born from the deaths of countless stars will merge into a single cosmic monster at the heart of a new galaxy. The name sounds whimsical, Milkomeda, a portmanteau of Milky Way and Andromeda, but there's nothing whimsical about the process that will create it. When two spiral galaxies merge, simulations predict the result will be a giant elliptical galaxy. Elliptical galaxies look nothing like spirals. They have no disk, no spiral arms, no organized rotation. They're bloated, football-shaped clouds of stars with random orbits. The overall structure is smooth and featureless, lacking the intricate beauty of a spiral. Why do mergers produce ellipticals? The collision destroys the organized rotation of the two spirals. Stars are flung in all directions by gravitational interactions. The orderly orbits that created the spiral arms become scrambled. By the time the merger completes, the stars are moving on random trajectories. Milkomeda will be massive. The combined mass will approach 2 trillion solar masses when you include dark matter. In visible stars alone, Milkomeda will contain roughly 1.3 trillion stars, making it one of the largest galaxies in the local group. Star formation will spike during the merger, then rapidly decline. When gas clouds collide, they compress and fragment, triggering bursts of new star formation. Millions of massive stars will be born over a few 100 million years. These stars will be hot and blue, giving Milkomeda a temporary bluish tint. But the star formation can't last. Mergers are efficient at using up available gas. The collision will funnel gas into the galactic center, where some will form stars and some will be consumed by the central black hole. Whatever gas remains will be heated to temperatures too high to collapse and form new stars. Within 1 billion years after the merger completes, Milkomeda will have exhausted most of its star-forming gas. Without new stars being born, the galaxy will gradually redden as its massive blue stars die and only the long-lived red stars remain. In 10 billion years, Milkomeda will be a red and dead elliptical, a galaxy composed almost entirely of old, low-mass stars slowly fading over trillions of years. But Milkomeda won't be alone. The Triangulum galaxy, the third largest member of the local group, will likely join the merger. If that happens, Milkomeda will absorb Triangulum as well, growing even more massive. Over the next 150 billion years, all the remaining galaxies in the local group will fall into Milkomeda. Dozens of dwarf galaxies. Leftover satellites, everything gravitationally bound to the local group, will eventually merge into a single giant elliptical galaxy. This is the future of our cosmic neighborhood. Not stars scattered across multiple galaxies, but one massive island of light surrounded by the expanding void of intergalactic space. Look up on a clear autumn night. If you're far from city lights, you might see a faint smudge of light in the constellation Cassiopeia. That smudge is Andromeda, 2.5 million light-years away, yet close enough to see with your naked eye. You're looking at light that left that galaxy when our ancestors were barely human. Before we built cities or wrote languages, that light has been traveling through space for 2.5 million years, crossing an incomprehensible distance just to reach your eye tonight. The James Webb Telescope has given us the clearest view of Andromeda ever achieved. We've peered into its core, seen the monster lurking there, watched gas spiral into the black hole, mapped stellar nurseries hidden by dust. What terrifies scientists isn't that Andromeda is coming toward us. We've known that for over a century. What terrifies them is what Webb revealed about the galaxy's current state. A black hole waking up, X-ray flares increasing, neutrinos streaming from the core, star formation accelerating in specific regions, galactic winds strengthening, signs of instability that models didn't predict. Andromeda is changing. Right now, in real time by cosmic standards, the galaxy we observe today is not the same galaxy it was 20 years ago. The black hole is more active. The core is more turbulent. Something is happening. Humanity will not witness this event. Our species may not survive the next few thousand years, let alone billions. Even if we do, even if we spread across the stars and become a spacefaring civilization, we'll face the death of Earth long before the galaxies collide. But the knowledge we've gained about Andromeda isn't for us. It's for whoever comes after the civilizations that might arise on other worlds, the descendants of humanity who will populate the galaxy in the distant future. They will inherit this knowledge. They will watch the collision unfold. They will witness the birth of Milkomeda, and they will remember that we were here first, that we looked up at the night sky and asked questions, that we built telescopes to peer into the hearts of distant galaxies, that we discovered the truth about our cosmic neighbor. Andromeda is coming. The black hole is waking. The collision is already underway at the scale of galactic halos. In 4 billion years, the night sky will be transformed. Andromeda will fill the heavens. New stars will blaze to life. The black holes will dance together before merging into one. And from the ashes of 2 galaxies, a new cosmic structure will emerge. That is our destiny, written in the motions of galaxies, inevitable as gravity itself.